So welcome you all to this ninth problem solving session. I'm going to wait for another maybe 1 or 2 minutes for others to join and then we can begin. So can one of you please confirm whether you can hear my voice and see the screen? You can write in comments also, otherwise I won't be able to understand whether you can see my screen or not. Okay, I'm assuming that you can hear me and also my screen is visible. If not, just stop and let me know. Okay, so let us begin. So in last week, if you remember, we discussed a lot about quantization, basically why quantization is important, what is the motivation. Of course, if you do quantization, which is we have to do by the way, what is the amount of information loss, how we can minimize it, what are the different techniques. Today we plan to go a bit deeper into that topic only regarding quantization. Maybe I will refresh some of the concept in the questions we are going to attempt first. So let us see what we have. So here we are given a uniform quantizer with 128 quantization levels and maximum message amplitude is given as 1000. So basically it is asked what is the quantization noise power. So all these concepts about what is a quantizer, what is a uniform quantizer, what are the quantization levels, the message amplitude and the quantization noise power I have discussed earlier, but for this week's participants maybe I will discuss in a bit more details. I'll just refresh that part. So let me choose the pen here. Okay, we have graphically seen quantization is something like that. So we have a continuous signal. Let's say this is what we call MT, and for the processing and all that we are basically going to sample it. And whenever we talk about sampling happen at a particular sampling frequency whose inverse is known as sampling time. So here what we are going to do, we are going to sample every TS instant. So TS, 2TS, 3TS, if I consider X to be time axis, and we are going to get these samples which I am marking in black circle. Sorry about that. example, this is MTS, this is M2TS, this is M3TS. So this is the sampling part. Now the issue is that the values we are getting, like those scalars, sorry about that, there was some networking issue in my end. Let me just okay, 5.4. Sorry about that interruption. I think you all can hear my voice and see the screen now. So I was talking about sampling here. So sampling is just a previous step of quantization. So the issue last time, as we discussed, the quantization is needed because the scalars we are having here, the samples MTS, M2TS, these actually theoretically can take infinite number of values. That is the issue. Because we have shown last time that if one sample can take infinite number of values, to represent it to a infinitesimal precision, you need infinite number of bits, and that you cannot afford, because the resources you have in terms of number of bits you can store in memory and the number of bits you can transmit, both are finite and limited. So that is where the quantization comes into picture. For example, you can these scalars can take let's say 2.31 and 3.49 and 4.92, like that. There are infinite possible values. So what I do, we do something like that. Let's say if the message signal takes value in this interval, I am going to map it to something like this. So this interval is being mapped to a scalar number. So the main motivation behind the quantization is you have to map the samples to a discrete number of values. The samples you are getting, that you don't have any control over, they can take infinite number of values, but what you actually can control over, you can map them to a discrete number of values, because you cannot really work with infinite number of values. So that is what the motivation behind quantization is. So since you are going to map samples which can take infinite values to discrete number of values, then automatically it infers that quantization is nothing but many to one mapping. So you can see here, if we look at this example, all samples in a interval is mapped to a unique value. This unique value, in more formal term, we call quantization level. And of course, when you are going to map all the samples in an interval to a particular value, that is quantization level, what you are going to introduce is something called approximation error. We discuss three cases for that. For example, you take any three value in this interval. Let's say I take three particular values, 2, 2.5 and 3. Now when the original sample value is 2, the approximation error is 0.5 because you are mapping 2 to 2.5. That is the error of minus 0.5 actually. For example, when its value is 3, your error is plus 0.5 because you are mapping 3 to 2.5. And when your value is 2.5, actually you are mapping it to 2.5, basically 0 approximation error. So quantization level inevitably leads to approximation error. Now the main goal is to how to keep this approximation error in check or in control. So how to do that? So for that we have to quantify the approximation error we are talking about. So how to do that? So let's start from the questions which mention uniform quantizer. Uniform quantizer. So uniform quantizer, what we have seen, let's say the quantization interval we denote as delta. So that means the gap between the quantization levels is actually delta. So for example, we are mapping this interval here, minus delta over 2 to delta over 2 to 0, then delta over 2 to 3 delta over 2 to delta, stuff like that. So that is what is seen uniform quantizer, which is the quantization levels, the gap, successive gap between the quantization level is a constant. Let me introduce a new slide here. And by the way, this is called delta spread uniform quantizer. So we see now that for delta spread uniform quantizer, we see that quantization error lies in the interval minus delta over 2 to delta over 2. That we can verify by picking any of this interval to some quantization level mapping. For example, here the quantization level is fixed at 0. The maximum error happens when it's delta over 2 because the gap is delta over 2. Minimum error is minus delta over 2 to 0, so minus delta over 2. By the way, The absolute maximum error is always delta over 2. So for uniform quantizer, you can see that quantization error is uniformly distributed. So that means if I plan to obtain the probability density function, that would look like this. So if I denote is that fq of small q, is given as 1 over delta when q lies between minus delta over 2 to delta over 2 and 0 otherwise. This is the plot here. This is the amplitude and this is the base, so that overall area should come out to be 1. Now we can define the quantization error as q as qm minus m. So this q we have discussed about in previous session. This is nothing but the quantizer function. So q is the quantizer. Basically it's a mathematical notation which takes the input m and output the quantization level. So basically q is a function and q of m is just nothing but the quantization level when the m is the actual sample value. So let me point those out. Quantized sample qm and m is true sample value. So you have expected value of q as, we know how, so q is a random variable and we know how to find the expected value of random variable when its PDF is given. You have to integrate over its range q f q dq, multiply the random variable with the PDF and integrate it over the range of its value. That's all. If I do that, this is a constant, it can come out, become 1 over delta. And then we have q dq integrated over minus delta over 2 to delta over 2, that is 1 over delta q square. 2 comes out here, evaluated at these two limits. This is delta square by 4 minus whole square, so delta square by 4 only, so it comes out to be 0. So the first order statistics, or the mean of the random variable quantization error, is 0. But that is not enough. We need to find the second order statistics also to fully describe random variable. So let us do that. Expected value of q square this you can call the variance of the quantization noise. This is one definition. This is also termed as quantization noise power, which we are supposed to compute. So let us do that. This is actually something that is being asked in the question. We are supposed to find quantization noise power. So quantization noise power is this term here, expected value of q square. So the procedure remains same. Only thing is that you have to integrate q square times the PDF and integrate over the variable range. Same procedure. This is a constant, comes out 1 over delta q square dq q square dq is q cube over 3. So we just take the 3 part outside. Inside all it remains is evaluating q cube at these two limits. We obtain those values as 1 over 3 delta q cube, that is delta over 2 whole cube minus delta over 2 whole cube. It will come out to be 1 over 3 delta cube 8 minus of this, so the minus will remain delta cube over 8, or 1 over 3 delta cube over 8 plus delta cube over 8. Sum them up, come out to be delta cube over 4. So 3 times 4 is 12 and in the numerator you have a delta cube and you have delta, so one delta cancel out, it's a delta square over 12. So we have obtained that quantization noise power is given as delta square over 12. But you don't know the delta here. So what are the values given in the question? You are given how many quantization level your quantizer uses, that is 128, and it's also given what is your maximum message amplitude, but the value of delta is not given. That you have to find it yourself. So we next will do that. We have talked about a function of this delta. Delta is actually function of both message amplitude and the quantization level, or to be explicit, it is a function of dynamic range. So let us look at that, what it is. So delta is your entire dynamic range, that is just a formal name for the interval over which the message amplitude varies, and that is divided by the number of quantization levels. So your dynamic range here, if we denote is as t, so your message belongs to this interval minus m max to m max. So therefore the dynamic range is maximum value minus minimum value, so that is 2 m max. So we have here 2 m max over L. L is the number of quantization level, or it you can see it as that number of discrete values. Both are actually same. So number of quantization level can be converted to number of bits required to represent each sample. We have seen that earlier. So you see that we have some L number of quantization level, number of bits required for L quantization level is given as log base 2 L. So if I denote the number of bits as B, this L can be written as 2 to the power B. So we can represent delta as 2 m max over 2 to the power B. So if I denote the quantization noise power here by, let's say, sigma q square, so that implies sigma q square is delta square by 12, so that is you have 2 m max over 2b whole square divided by 12. That means 4 m max square by 12 2 to the power 2b. Remember, it's 2 to the power b here. Sorry, I have written it as 2b. Actually 2 to the power b. So that's why this 2 parts comes in exponent only. So that means it's given by m max square divided by 3 into 2 to the power 2b. So that is our quantization power with respect to the maximum message amplitude and the number of bits required. So it's easier to represent in, this is in linear scale here, this is in linear scale. So it turns out it's actually pretty easy to talk about this noise power in dB scale. So if I talk about the quantization noise power in dB scale, so I denote it as, let's say, sigma square q dB. that is given by 10 log base 10 sigma q square value in the linear scale. So if I write 10 log base 10 m max square divided by 3 times 2 to the power 2b. So what we have, first term it's m square, 2 can come out, so it's 20 log base 10 m max, 3 is below, so it would be minus 10 log base 10 3. Same applies for 2 to the power 2b, so it would be 20b log base 10 2. Now let's put the standard value of log base 10 2 is around 0.3. It's actually 0.301, we can approximate at 0.3. If I put it there, we'll get 20 log base 10 m max by the way. This 10 log 3 value, 10 log base 10 3 value is around 4.77. so let us put that minus 4.77. here I have 0.3 times 20b, so 20 into 0.3 is 6, so it's 6b. So you can see in dB scale things become much more apparent, in the sense they are affine function in the message amplitude and number of bits. So you can see here linear function of maximum message amplitude and number of bits in quantizer. So just we need to now put the values. So what we seen here is that we have 128 quantization levels. That means B here is log base 2 L, that is log base 2 128. We know 2 to the power 7 is 128, so basically B is 7. So we need 7 bits per sample for this particular quantizer, which have 128 quantization level. And M max is also given, the maximum message amplitude, as 1000. So for this particular case, if I put these values, sigma square q dB comes out to be, if I put M max here, that is 20 log base 10 1000 minus 4.77 minus 6 times 7. So this one here, log base 10 1000 is 3, so 20 times 3 is 60, minus 4.77 minus 7 into 6 42. That means it would be 18 minus 4.77, that is 13.23 dB. So this is going to be your quantization noise power. So let us just see which one of the answer matches. So the fourth one is the answer. So that's how we can get the quantization noise power in dB scale. Okay, excuse me for a minute. I'll be just back in a minute or so. Okay, let us move to our second question. So second question is about it is asking the bit rate of T1 system. So what is the bit rate supposed to be? So for this question we need to have bit of idea of what T1 system is. It's actually quite used to be popular. Nowadays we may not have heard of it, but T1 system is telephony system. So how it works, basically we discuss in terms of a model question we discussed in previous session. So T1 system is something, let us call it telephony system. It works on the principle of time division multiplexing. So basically goal here is to combine multiple uh, low frequency signals in time domain to generate a, sorry about that, to generate a high frequency composite signal. So the idea is you have the same channel, so your channel resource is kind of limited. So what you are planning to do here, basically multiplex the uh, multiple low frequency signal to create a high frequency signal that you can transmit over the channel. That is the goal. So the multiplexing has this advantage that at a time you can send multiple signals in the over the same resources. That is the main goal. So that system in consideration here, that is a T1 system. It multiplexes 24 voice channel over two separate wire and transmit them. So you are not going to focus over this two separate wire part. You have basically focus on this 24 voice channel. It is going to multiplex. That is the goal of T1 system. So how it works, basically, if I give a graphical representation, it might be easier to understand. So you have, let's say, multiple low frequency signals such as M1T, M2T, up to, let's say, MNT. So you have capital N number of signals. So what you are doing, you're basically passing them through a low pass filter, just to make sure the high frequency components are not going to be there to create any issue. You pass them through low pass filter, and then you do what you do. You basically going to use a commutator to collect all of them. So commutator is something like this. You can interpret as, so this is commutator. So the thing is that at a time it picks a sample from this line, then it rotates, pick from this, then it pick from this line, like that. That's how commutator works basically. So here you get the composite signal. Okay, there is a signal problem. Videos are presenting. Okay. Can others please also confirm, is the same thing happening to you also, like you are not able to see my screen properly, or my voice is breaking, something like that? You can just confirm in chat box. Okay, I'll do one thing. I will turn off the video just to make sure that that is not the issue, and to reduce the bandwidth basically. And so just let me know if you are this issue like remains. I'm expecting that you will not face the issue, because now I have stopped my video, so my screen is the only thing that is going to be visible. So that should reduce the bandwidth requirement, so your signal should be better. Just let me know if it's not happening. Okay. So yeah, we are discussing, we are basically taking the multiple low frequency signals, trying to multiplex them. And how to multiplex, we are basically using a commutator. How it works, we will going to discuss in a minute later. And then we obtain here the composite signal, and we are going to transmit over the channel. At the receiver side, the opposite happens. So this is the stage where you are actually going to multiplex different message samples. Let me introduce a slide here. Okay, it's still buffering and video is like 144p. Okay, it would be nice if others also please confirm if they are facing the similar issue or for them it's okay. Otherwise I'm afraid there is not much I can do from my end, because here though I'm not facing any network issues, and since I turn off the video it's smoother in my end. Apparently there is no network issue in my side, so I'll just do one thing. I'll just stop the presentation and start presenting again. Just see whether it improves. So this sampling part, or the how commutator works, let me explain it a bit more. So it's like that. Let's say you have a 3 message signal. Like let's say this is for M1. This is the axis, by the way. This is M1 here. This is M2, and this is M3. So this is M1, this is M2, and this is M3. So what is happening here? I am going to sample each one of them, M1, M2, M3, with a gap of Ts. This is basically my sampling interval. This is my sampling interval between any two samples of any of this message signal. So this is my sampling. 1 over Ts is my sampling frequency. This is Ts. So how should my composite signal should look like? Something like this. Composite signal, which is basically made up of all these samples, something like this. So let's talk about the Tsth instant. Let's say this is Tsth instant, this is also Ts, this is also Ts. So this one here is M1 Ts, this one here is M2 Ts, this one here is M3 Ts. Similarly, there are n such thing Mn Ts. Now the interesting thing about the composite signal is that that entire window here has the interval Ts. Why is it so? Because in this Ts interval it has to collect the samples from all of them, because the moment Ts interval is passed, the commutator should go back to M1, because at M1 end M1 2 Ts has already arrived. So you can see here, whereas for individual message signal there is only one sample at every Ts instant, composite signal is multiplexing all the message signals. So basically in TS instant it has n number of message samples. So the duration between samples in time division multiplexed composite signal is TS over n. So I was talking about each of this gap. This is TS over n. Because you are going to cover n number of samples in the TS instant. Cover n samples in TS instant. So you can also intuitively see that kind of the sampling frequency of the composite signal now become n times. So the receiver side, just to give the clear picture, your composite signal comes, and what you use something like another commutator, we are denoting as CR. Let's denote the previous one as CT here. This is we are calling CR, and CR job is just as opposite, like that is each of this line and corresponding LPFs here. So if this if CR and CT are synchronized, and by the way they have to be synchronized, otherwise the entire thing fails. So here we are going to get estimate of M1T, estimate of M2T, M3T, like that. Here CT need to be synchronized for error free operation. And one thing, CR actually is delayed by TS over N compared to CT. And intuitively the reason is that even though that composite signal we are talking about that T1 which multiplexes 24 channel, here let's say n is equal to 24, actually it's 24 message signal information, 24 different channels. On top of that it transmits something called synchronization pulse, which doesn't carry any information like useful information, so that is not counted as part of your data, but it's actually contain something very useful, that is synchronization related information. So this is why the CR is delayed by TS over N, because it has to ignore the synchronization pulse. So let us insert another slide here just to continue the discussion. So now T1 system bandwidth, you can already intuitively see how it is. It is going to be 24, since you are multiplexing 24 voice channel, it's 24 times voice signal bandwidth. By the way, I am multiplying it given that voice signal bandwidths are all same and identical. If they are not identical, the multiplication won't be valid, you need to sum it. But since this I am assuming all voice signals are identical, their bandwidth are same, I am just taking the 24 as a common. That's the reason. So if I put things in a context of T1, the sampling interval for, so remember we have to compute what need to compute. Let's just move to the question. We have to compute the bit rate, and to compute that we have to proceed in a methodical way. That is, we have to find the sampling interval for each of these voice signal first. So it's, if I draw the analogy here for any random signal, let's call it TS. Now we have to find the what is the voice signal frequency range. Voice signal frequency range. If you check, it would actually come out to be voice signal, no matter what kind of voice signal it is, it's going to be between 300 Hz to 3.1 kilohertz. So if you consider that DSBSC kind of modulation, so your spectrum of voice signal in the visual will look like something like this. Sorry, not DSBSC, before modulation, the baseband stuff, it's going to be between here to here. So just remove this part here. This is, let's say 300 Hz is minimum and 3.1 kilohertz is the maximum. So this is your voice signal frequency range. So you can see here that your maximum frequency content is 3.1 kilohertz. Therefore you can immediately find the Nyquist frequency. If we call it Fm here, your Nyquist frequency Fs is going to be 2 times Fm, that is 6.2 kilohertz. That is the borderline. So basically that says, if you want to protect the amount of information, you need to sample the voice signal at or over 6.2 kilohertz. But of course that is under ideal condition. So in practice we always need to keep a safe amount of like margin, a healthy margin. You cannot go by the borderline Nyquist rate, because that is for the ideal scenario. In practice ideally doesn't hold, so you should always have a safety margin. So what do you do here? In practical scenario, your sampling frequency for voice is given as Fs as 8 kilohertz. Now you see that we have already talked about in the previous slide what is the spacing between the time division multiplex signal, Ts over n, right? So spacing between consecutive samples of T1 composite signal is, let's call it T, it's Ts over n. Therefore the bandwidth you will require, bandwidth required for transmission of the TDM of T1 composite signal So remember that T1 composite signal have a sample at an interval of Ts over n, right? So for this the bandwidth requirement of course is 1 over 2t, right? That is 1 over 2 Ts by n, or n by 2 1 over Ts. Okay, actually sorry, I should okay, fine. Bandwidth required for a composite signal 1 over Ts fs by 2. Oh, sorry, I made a mistake here. It should not be, it should be T over 2. Sorry. Your sampling frequency is T, it should be 2T over 2. That is 2n here. That will be 2n. Just fix that. 1 over Ts by 2n, that is 2n over Ts. Since your Nyquist frequency for individual message signal is greater than 2 FM, that means your composite signal FT1 should be greater than n times FM. Sorry, n times 2 FM. N FM. Now you have to know in T1 signal what kind of quantizer you have to is used. Otherwise you cannot find really the bit rate, because then as long as you don't know the quantization level or how many bits are used to represent per sample, you'll never know what is the amount of bits that is required to be transmitted for T1 system. So that is important also, the information that how many bits per sample, and that information comes from the quantizer, your quantizer. What kind of quantizer you are using, a quartz one which use less number of bits, or a quantizer with a finer resolution which use more bits. So T1 system uses mu law quantizer. What is that? You can refer to that lecture actually. So what is important here to know is that mu law quantizer, it uses with 256 quantization levels, and that is our useful information. So the number of bits is number of bits per sample, number of bits per sample is given as log base 2 256 or 8. So we have seen that sampling frequency for voice signal, what is that? Fs is given as 8 kilohertz. Okay, here I have forgot that Ts is a sampling frequency here, so there should not be any Ts over 2n, because that is already been factored in Ts here, so there won't be any 2 here, it's just 1 over T. So these two parts won't be there, it's just n. because it's just n time fs. I was thinking in terms of fm, but that was wrong. It's n time fs. The sampling frequency for each voice signal is 8 kilohertz. That implies your sampling interval is 1 over 8 kilohertz, that is 125 microsecond, right? And we have already seen from this slide here what is that. TS is 1 TDM frame duration, right, which contains basically those symbols. So this here is T1 system frame duration, one frame duration. And one frame, how many samples it contains? 24, right? But that is not actually true. Total number of bits per T1 frame. Remember we talked about synchronization pulse, which makes the gap between the commutator and receiver and transmitter side by Ts over n, and that is because I mentioned that there is a one pulse which doesn't carry any useful information from the data perspective, but for synchronization it is very useful because it is used for synchronization task between the commutator and receiver and transmitter side, which is essential for the error free operation. So actually what it does, in each frame you transmit 24 message samples plus one synchronization pulse, one synchronization pulse. So total of 25 bits. Okay, sorry, 24 message sample plus one synchronization pulse, right? That means how many bits for each sample? We have talked about 8 bits. 24 times 8. Synchronization pulse doesn't require 8 bits. It's a 0-1 decision, like 0 or 1. So basically you just need 1 bit for it. So remember, synchronization pulse doesn't require 8 bits because it is not passed through quantizer or something. It is just a binary decision, 0 or 1. So that is why this synchronization pulse is there. So total you need 24 times 8 is 192 plus 193 bits. So in one frame of T1 there are 193 bits and one frame duration is 125 microsecond, right? So number of bits sent per second for T1 is given by, if 193 bits is sent over 125 microsecond, how many is going to be transmitted over 1 second? You can just use class 10 math here or class 8 math. You have 193 bits every 125 microsecond. So this many number of bits are going to be transmitted per second. So bits per second is your bit rate actually, right? So this goes there, 193 by 125 megabits per second, that is your bit rate, and this ratio is, let me just calculate, 193 divided by 125, that's 1.44 megabits per second. That is the bit rate of T1 system. Let us go back to our question here. Sorry, my calculation was wrong. It's 1.544. Sorry, 1.544 megabits per second. So the second one is your answer here. To answer this question, you are supposed to know how many symbols are multiplexed in T1 system. You are also supposed to know there is one synchronization pulse, and you are supposed to know that T1 system use mu law quantizer with 256 quantization levels. Only if you know all these three things about the system, then only you can answer this. So just remember these numbers in case you have some question regarding 51 system where those values are not mentioned. So let us move to our next question. I remember I was discussed something about the kind of receiver in last session also, but let's look into more details this time. So we are talking about super heterodyne receiver with intermediate frequency f2. What is the frequency of the local oscillator corresponds to an incoming signal of carrier frequency f1. By the way, even if I talk about super heterodyne receiver last time, I'll just refresh that topic here. So by the way, what is the purpose of this? What is this whole thing is known at? Let's say you have a incoming signal here. Incoming signal of frequency f1. At the receiver side, you have a local oscillator which has a frequency f2. You are basically using this and obtaining this IF for intermediate frequency. So this entire procedure, this entire thing is known as frequency mixing. So basically, why frequency mixing? You can see you are mixing the incoming signal has a certain frequency, your local oscillator produces a certain frequency f2, and you are mixing them to get some derivative in terms of f3 or something. So the question here is, what is the purpose of this frequency mixing here? So what frequency mixing actually do? It shifts the received signal to a new center frequency. This center frequency is known as intermediate frequency. So the purpose is that often you receive the signal, often signals are actually transmitted over the high frequency carriers, right? That we have already seen. And what is the purpose for that? So when you transmit over it high frequency carriers, actually what happens if you don't shift it to, you remember that frequency content is centered around the carrier frequency, which is very high value in terms of gigahertz. So if you try to process the raw incoming signal at that carrier frequency, at high frequency, actually your instruments that you are using at the receiver end for processing is very expensive. So to avoid that, what you need to do, you are going to use some inexpensive equipments which will only work well in a low frequency, right? So what you need to do, you need to change the center frequency. The incoming signal has, let's say, a center frequency of, let's say, 2 gigahertz or something, but your equipments that we have maybe can act as a carrier frequency of like 500 megahertz or something, not beyond that. So what you can do, you need to bring down the center frequency of your incoming carrier wave to 500 megahertz, so that the equipments at your receiver end can process that signal. So that is the whole point of frequency mixing. So that's why the intermediate frequency is always going to be lower than the incoming signal. So the idea is that something of this sort. So if I see for before transmission what is happening, so you have this message signal, the baseband version. Let's say this is FM, this is this is baseband message. Let's say this FM is 100 kilohertz or something. So when you transmit it over, you don't transmit as it is. Of course, you have seen this. You first modulate it on a higher carrier frequency and then transmit it. So you transmit it something like this, and this centered around FC. Let's say FC is a very big value. Let's say it's 1 gigahertz or something. So you transmit it, fine, no issue. But when it comes to processing at the best, at the receiver end, you again need to bring it down, right? So what you do frequency mixing. You bring it down to a lower carrier frequency. Let's say something like this. This is what is called IF, or intermediate frequency. So FIF value is less than FC. That is the whole purpose. So what you do after, just let me write it down. After frequency mixing, the signal is amplified, filtered and demodulated. So if I try to draw that thing here, the same thing, just with a bit more. Actually, I will not draw this here, so just modify one of the modules in the top one here. So here we have a this thing which I have earlier not clearly mentioned. This is actually a band pass filter which is centered around FIF. So your incoming signal is like F1. Let's say it's MT cos 2 pi F1t. Local oscillator is generating a carrier wave at frequency F2, so it's cos 2 pi F2t, doing the product here, which is calling frequency mixing, and we are getting some content, right? So let's see what we get here. Here we have MT cos 2 pi F1t cos 2 pi F2t. So if I do the basic trigonometry, what I will get is MT over 2 cos 2 pi F1 plus F2 t plus cos, sorry I missed the 2 pi, okay, 2 pi, what is that, 2 pi F1 minus F2 t. Did I write it correct, or should be F2? Okay, it should be F2 minus F1. F2 minus F1. Yes, if you have some question, please ask. Okay, after mixing, how many frequencies are produced? Which one is selected at IF? Okay, there are actually just I am going to discuss, but let me clarify here. You can see there are two frequencies that they are going to produce, right? F1 plus F2 and F2 minus F1. Now let's say if you choose the intermediate frequency as any, like I am going to pass any one of it. Let's say if I use a band pass filter with a frequency f1 plus f2, it is going to pass the first term, and if I keep the band pass filter with a frequency f2 minus f1, it is going to pass the second term. Now my question is like which one you want to be the intermediate frequency? I mean, the entire goal of frequency mixing is to bring the carrier frequency down so that your processing is inexpensive, right? So which one we are supposed to choose? You can choose actually theoretically any of this. So always in intermediate frequency we are going to choose that f2 minus f1 term because that is lower than f1. So that is what going to be our intermediate frequency is, because then in the scenario we are going to bring our center frequency down for improve the ease of processing. So you can see here, as you mentioned, that this is a frequency component which is centered around f1 plus f2, and this is a frequency component centered around f2 minus f1. You can pass any of them, but since the goal of the intermediate frequency is to bring the carrier frequency down, so intermediate frequency should be lower than the carrier frequency. That's why you are going to choose a band pass filter with this frequency f2 minus f1. Let me introduce a new slide here. So if you pass the earlier signal through the band pass filter with frequency f2 minus f1, we are going to receive this. And this is going to be my intermediate frequency FIF, that is f2 minus f1. Now you can see that the choice of f2 actually we have written that f2 minus f1 as FIF. So the f2 can be FIF plus f1, but you can see other way around. I can write it as f1 minus f2 also. It doesn't really going to change because cos of minus theta is cos theta. So in that scenario, this is going to be your intermediate frequency, same, but in that case your oscillator frequency f2, this is local oscillator frequency, and this one here is same. So f2 in that case is going to be f1 minus FIF. So there is one scenario, let's say this is 1, this is 2. In this scenario, your local oscillator frequency is greater than carrier frequency, and in this case your local oscillator frequency is lower than your carrier frequency because it's f1 minus FIF. So in these cases the intermediate frequency remains identical, but it's just what the local oscillator frequency we are going to choose, and that is what like the distinguishes the receiver. So this scenario, the first one, is known as super heterodyne receiver. Super heterodyne receiver, because the local oscillator frequency is greater than carrier frequency, so this corresponds to super heterodyne receiver. And second one, when local oscillator frequency is less than carrier frequency, this is termed as heterodyne receiver. Heterodyne receiver. So if you see any question in maybe in assignment or in the final exam, and they have like this idea like intermediate frequency is given, carrier frequency is given, you are asked about the local oscillator frequency, and you have to check whether they are asking for super heterodyne receiver or heterodyne receiver, because for different kind of receivers the carrier frequency will remain same for you, intermediate frequency will remain same, but the local oscillator frequency is going to be the distinguishing factor between different types of receivers. So you have to be careful whether it's asking for super heterodyne receiver or only heterodyne receiver. So in our question it's a super heterodyne receiver, so it is supposed to be, let us just go back, yeah, your local oscillator frequency is going to be f1 plus f2, where okay, one thing, okay, I mixed two things. I mentioned the local oscillator as f2, so even if the answer is correct I should change the notation here. So this is f2, this is f2, let's call it f dash here, otherwise it's going to create confusion. It's f dash, this is f dash, this is f dash, this is f dash, f dash, f dash, this is f2, this is f2, this is f dash, f dash, f2, f dash, 2. That is, the discussion I did will remain same. It's just the notation would be misleading in case someone is watching this for the first time, because just to don't confuse it, like the f2 is now intermediate frequency and f dash is some local oscillator, and we obtain the expression of f dash for super heterodyne receiver. It's always greater than the carrier frequency, so it's going to be always f1 plus the intermediate frequency f2, and had it been heterodyne receiver it is the opposite way around, it's just the carrier frequency minus the intermediate frequency. Okay, let us move to our next question. So this is a uniform quantizer with the 1024 quantization level and maximum message amplitude is given as 200. What is the quantization noise power? So we have solved the similar question earlier. So let us just write down the quantization noise power in dB scale is given as 10 log base 10 sigma q square is minus 10 log base 10 3 plus 20 log base 10 m max minus 20 b log base 10 2. B is the number of bits to represent each sample. So this value we have already seen is minus 4.77. This is going to be 20 log base 10. You just put the values. This is 200 minus, this is 20 log base 10 of 2 we have seen it's 0.3, so it's minus 6b. So it's going to be, b is log base 2 number of quantization level, which is given as 1024 here. So it's log base 2 1024, that is 10, because 1024 is 2 to the power 10. So minus 4.77 plus 20 log 200 is 20 log 100 is actually 40. So 40 plus 20 log is 10 2 minus 6b, that is 6 into 10. This is again 0.3. So it's minus 4.77 plus 40 plus 6 minus 60. So this is going to be plus 46 minus 64.77. So that is 46 minus 64.77, that is minus 18.77 dB. So let us just see which one is the closest. First one I see is closest, minus 14 minus 18.75. It's a gap of 0.02, so this is the correct answer. So this question is about T1 system is an example of frequency division multiplexing, code division multiplexing, space division multiplexing, or time division multiplexing. So we have already seen in T1 system what we do is we multiplex multiple voice signals in the time domain. Basically, if the time domain for each sample, for each signal we sample with a sampling interval of Ts, then the T1 the composite signal in the T1 system has a frame duration of Ts, but within this Ts sample it multiplexes n different samples from different message signals. So it's a time division multiplexing. It's a multiplexing in the time domain. This question about in the delta modulation, the distortion that arises when the step size delta is large in comparison to a signal that is relatively flat, what is going to term as. So this delta modulation we have discussed in details in the previous session. In case you can check that out. So this is nothing but differential this is differential modulation scheme. So basically here the plan is to, you instead of quantizing the raw value of the sample, you just quantize the successive gap, you quantize the difference between successive samples. So in that way the values comes down drastically. So you just, for a same error, you can use actually much less number of quantization levels. So that essentially translates to less number of bits per sample, which basically saves your resources. That's the whole idea. So this I am not going to discuss in detail, you can refer to previous video. So I'll just draw that what actually is going to happen in this case. So it's said that message is relatively flat, so you have a message like this, so which is not having, you can see the slope is very low. But when you have this high step size, so what is happening in that case, you are going to have problem in message reconstruction, because it will look like this. And if you have a lower step size, you can actually have this. So what is happening in the delta modulation, if you use a 1-bit quantizer, so every step size, this size here is of gap delta. So what happens is that you do something called staircase approximation. So to understand how it works, you need to have idea of three terms. First is mqn-1. This is your quantizer prediction of sample at nth time instant. So this quantizer is going to predict this value for nth time instant, or you can say this is the reconstructed value at nth time instant, and mn is the true sample value. It is the true sample value. So of course you have reconstructed something, mq n minus 1, and this is the true value. So of course there is going to be always an error. This is denoted as mn minus mq n minus 1. So this is your error. So what you do, you quantize this error. So you quantize this error u of n, which you denote as eq of n. This is, let's say, en, and since you are using 1 bit quantizer, it's just the sign of this error times the step size, and sign means sign of x is 1 for x greater than 0, and sign of it's minus 1 when x negative. So what is happening here? So let's say this is your reconstruction, and this is two sample values here. So your error is negative. So what is going to happen? Quantizer is going to do is going to your prediction at the next instant is going to be minus of delta, because the sign of error is now negative. So it comes down to here. Now when it comes down to here and the true sample value at this point comes out to be higher than this, then what will happen? Your error is going to be positive. So it's going to be actually step up by what amount? By this delta amount. So when the message slope is relatively flat, I mean it's not changing much, but your step size is very big. So what is happening? You are going to have this kind of problem. You are like what should I cause, like unnecessary fluctuations in your reconstructed value. So you have unnecessary fluctuations in the reconstructed signal when your message signal is relatively flat, but the step size delta of quantizer is large. That is the issue, and this is termed as granular noise. The opposite scenario, when the signal slope is quite high, that is it moves drastically, and you have a small step size, like a smaller, so of course it's a relative thing. So you have your reconstructed signal has a difficulty to catch up with the original signal. In that case, something happens. It is called slope overload distortion. So slope overload distortion can be graphically shown as this. For example, your message signal increases like this, and your step size is small. So you basically your approximation is this. You fail to catch up to this high values because your step size, every time your step size is small, and by the time you catch up, the signal has already increased. So that error increases as that time instant increases. So that's just the opposite thing of granular noise. Sorry about that. It's, briefly it goes out of connection. I think now it's okay. You can see my screen right now. No, thank you. Thank you. So let us move to our next question. It asks about a superhead receiver with broadcast frequency FC and intermediate frequency IF. So it is asking what is the corresponding image frequency going to be. Remember the structure here. Your modulated signal comes here with the carrier frequency 2 pi fct. You do the frequency mixing part by local oscillator cos 2 pi fc plus fif. Since it's a super heterodyne receiver, the local oscillator frequency is carrier frequency plus intermediate frequency, and then you use a band pass filter, center frequency around FIF, and you get your message signal of mt cos 2 pi FIF t. But that is not the only signal that is going to produce this intermediate frequency. There is going to be something called image frequency. Let's call it f dash. So if let's say we have instead of mt cos 2 pi fct, we have cos 2 pi f dash t. So let's say what will happen in that case. We have mt cos 2 pi f dash t and cos 2 pi fc plus fif t. So this is going to be divided into two parts, of course. One is cos 2 pi fc plus fif plus f dash t. Another is cos 2 pi f dash minus fc minus fif t. Now if for some reason this f dash, for some value of f dash fc, let's consider f dash minus fc minus fif is this pass through this band pass filter, and when it will pass through this band pass filter, when this frequency is equal to fif, right? So this frequency content is going to pass through the same filter when this value actually equal to intermediate frequency. So that means if f dash is equal to fc plus fif plus fif, that is fc plus 2 fif, then this signal with this carrier frequency is going to pass through this band pass filter by creating noise for the original signal. So that is the issue. The super heterodyne receiver phase and the corresponding image frequency is given as fc plus 2 fif. Let's ask whether two events are mutually exclusive, then which of the following statement is always true. So it's always better to answer this question by drawing sets. Like if we draw two mutually exclusive set, let's say this is A and say this is A and this is B. So these are mutually exclusive in the sense there is nothing common between them. So if I do A intersection B, you are going to see that is a null set. So it basically contains nothing, and probability of null set is 0. So basically probability of intersection of A and B is 0. So you can see there is only one option, and that is this. Let's check another ones. First of all, P A union B is not going to be 0, of course, because let's say this is a bigger set, like it is the entire subset, and this A and B are subset. So first of all, P intersection B1 is wrong, because we have already shown P intersection B is 0. Now P A union B, can it be 0? No, it cannot be, unless and until A and B are themselves null set, but then it violates the principle that A and B are mutually exclusive, because if A is a null set, then B cannot be, and vice versa. So this is also out of picture. 4 is also out of picture. What is the third one? Third one says that P A union B is 1. So this can or cannot be true. It really depends. For example, if A and B are like, let's say, if I draw this diagonal line, say this part is A, this part is B, then in that case it will be fine. But it is not guaranteed, so you cannot say that from this information. But when it comes about like says about always true, it should be something that directly infers from the information here, and that is only about that. The second one is only true. If A and B are mutually exclusive, their intersection is always going to null set, so and probability of null set is 0 always. So let us move to our next question here. So this is only similar. You have uniform quantizer, 256 quantization levels, and you are given the maximum message amplitude 500. So quantization power in dB scale. So we have already seen. So let us just put the values here. So 10 log sigma q square is minus 4.77 plus 20 log m max, and then minus 6b, right? That is minus 4.77 plus 20 log 500 minus 256 quantization levels means number of bits required is 8, so 6 times 8, that is minus 4.77 minus 48 plus 20 log 500 is 53.97. That would come out to be 1.21 dB. So the third one is the correct answer. So with this I plan to conclude today's session. If you have any questions, you can ask me. And thank you all for being here throughout the session. So if you have some questions, please ask. Thank you. So if there are okay, so if there are not any questions, we can conclude this session, and we'll meet again on next Saturday. Thank you.